Okay, so if you recall, last week we discussed we briefly introduced the CNN concept. So convolutional neural network, and it's pretty good for image classification. Okay, and generally speaking, CNN, it consists of a number of, we call it conv layers. And after that, normally we have pooling layers. And normally we put both together, okay, and you can repeat, okay. And then we can have flattened layer. And then the last is fully connected layers, okay. So that's the, if you recall, is it? And CNN, as we also discussed, it is really good for extract features. Okay, so we also call it feature map. Okay, so that's the convolutional layers. Because we can use a filter, is it? And it depends on what type of filter you provide, is it? If you recall, we can do like horizontal edge detection, vertical edge detection, etc. Is it? So those edge detection, basically, it's regarding features in the images. So that's what why we see the CNN is the convolutional layers. It can extract features. Okay, and the purpose for the pooling layers is to bring down, as to decrease the size. Okay, decrease size. So just get the most salient elements. That's the purpose of pooling layer. Okay, and then we do flatten, because just generally speaking, CNN after the convolutional and the pooling layers, then it's 3D. It's 3-dimensional. Okay, so you have height, weight, and you also have the number of channels, etc. And each channel, so generally speaking, the 3rd dimension is for the features. So that's why you can have multiple filters. And each filter can detect one kind of feature, okay? But when we do, if you recall, when we do neural network, we need to flatten it to 1 dimension, is it, and make it then fully connected. Okay, so that's why at the last stage, we still need to do the flattening, okay? So that's just a general idea about convolutional neural network, okay? A recent number of years, it's developed pretty advanced and efficient also, okay? So we will see. And it sets images. We already see, as if you recall, the MNIST. That's a very basic and classic image data set, as if handwritten digits. Okay, and generally speaking, it's grayscale pixel data. Okay, so that's why normally we also add a channel dimension. So that's why it's 3-dimension. The 3rd dimension is a channel dimension. Okay, and for the channel dimension, the channel can represent the color channels of the image data. okay. And also based on previously, we already saw that normally pixel values is in the range of 0 to 255. So that's why normally when we do neural network training, and generally speaking, we needed to scale it to 0 to 1, okay, to do the training. Okay, so that's the very basic concept, okay, about convolutional neural network. Okay, so next let's take a look at example. Okay, using CNN for image classification. Okay, so basically right now it's also this, the CNN concept is also used for object detection like face recognition. Okay, quite a lot. And for the MNIST, we use TensorFlow Keras data sets, okay, because it's already pre-processed. And if you recall, the Keras, TensorFlow Keras, basically it's a Keras, okay. So Keras is a high level, okay. So high level API, so that we don't need, so no need to define the graph. The TensorFlow is built upon graph, so there is no need for us to define the graph, the node, and the edge. There is no such necessary, okay. And generally speaking, for Keras high-level API, there are two types. One is sequential. So sequential is a layer by layer. The other one, if you recall, is called function. Okay, we over here discuss about sequential. Okay, and to use convolutional neural network in Keras, then we need to import the packages like the layers package. Okay, and it has the definition for the like dense layer, convolutional layer, pooling layer, and the pooling there are multiple different ways. Okay, this max pooling is, if you recall, so after you have the grade, that it's a pick the maximum one. And we can also do mean one. There are some other pooling. Okay, and we can also do flatten. And if you recall, the drop off is to purposely add 0 to weights. Okay, so it's based on probability. So that when for the fully connected parts, is it, and in order to avoid overfitting, okay, so we can add also a dropout layer. Okay, so that's just a quick recall. Okay, so then, so first we just load the data, so that's pretty easy to understand. And also we try to get the features. This is regarding features shape. Is it the features? So here is the shape, okay. And for convolutional neural network to work in TensorFlow, we need to also have channel data, if you recall the third dimension. So that's why over here, we need to reshape it for the third dimension, okay. Then after it, you have the, and the third, only one channel in this case, okay. And the same thing for the testing data, you also need to reshape, okay. So just be careful. And we also want to know how many different images we have, different types. That's why you can do the unique and to get it. And here we can see it's 10, is it? And then we also do normalize our pixel data. So that's why over here you divide by 255, okay? Bring your data to the scale of 0 to 1, is it? Okay, so this part is just doing some data pre-processing, okay? And then for CNN, we still use sequential model here, okay, sequential. And the image size right here is 28 by 28. This one is a third dimension, okay, third dimension. And over here, it says, so in this model, in our first convolutional layer, we'll have 32 filters. So that means you can kind of extract 32 features. Okay, 32 filters. Maybe you have horizontal edge, vertical edge, diagonal edge, some other stuff, is it? So each filter match like one kind of feature. Okay, so this is a number of filters we are going to use. This kernel size basically is defines the filter size. So filter is a patch, a small patch, and then you do the sliding, is it based on the stride. And if stride wise, just move 1 pixel. Is it if it's 2, then every 2 you move as you jump. Is that so? The filter dimension in this case is 3 by 3 by 1. And also be careful, okay? Initially this third dimension should be the same. Okay, so filters dimension and the image dimension should be the same. Okay, we need to be careful. And after that, then we have the output layer dimensions at 26, 26, and increased to 32. Is it the height and the weight size got decreased? Is it? And the dimension, the third dimension increased. So the channel increased. Why? Because of the features. Is it you want to extract multiple features? Is it? Okay, so that's the general idea. So let's see, okay. And we can add layer by layer to sequential model. Okay, so the first one we are going to add is a convolution layer. Is it? So the first parameter 32 is the number of filters. This second one is the filter size. And you also need to pick what is the activation function. So here we use rectified linear unit. Okay, and this kernel initializer is just to how to initialize the weight. So here we pick some small random number, but make the distribution follow this heat distribution, okay? And it also defines the input shape, okay? So let's see, the input shape is defined by that in shape, okay? And the in shape we already defined, is that based on the previous, over here we reshaped, so. Okay, so that's the first layer. And the corresponding, normally you have convolution and you have a map matching a pooling layer, okay? And then we have the maximum pooling layer. So the pooling layer, you use 2 by 2 patch, okay? So 2 by 2, then from 26, is it decreased to 13 by 13 and 32. The third dimension, you still keep the same, is it? So you have convolution like this size, is it? And then go back here, then it's decreased by 2, is it 2 size? But the number of, so you're totally going to have So we have 32, is it the third dimension, 32. So same thing here, okay, you are also going to have, oh, I should dash, okay. Then here is dashed. Is it so total? You should also have 32 filters, channels. Okay. So this is so initially, this is initial. That is 32 by 32 by 1. Is it? And you have convolutional layer, and here is a pooling layer. Is it? And you increase the third dimension, but for the other two dimensions, it's decreased. Okay, it's decreased. So generally speaking, we get this two as like you extract certain features, is it? And after that, we do flatten. So flatten, make it back to one dimension, is it? And then you have that, then we need to make it to squeeze it to size 100 neurons. So here you have 100 neurons, is it? And the last step is you have 10 digits, is it? So, and then, so that's why you add another dense, is a number of classes, okay? And also over here, when we convert it back to one dimensional, we also need to pick activation, is it? Activation. So the activation function is we still use rectify. So generally speaking, rectify linear unit is good for activation. So it's better. So performance is better than sigmoid, okay? If you recall, sigmoid can also be used for activation function, okay? But be careful, okay? Generally speaking, at the last layer, we don't use rectify linear unit. We use softmax, okay? And if you recall, softmax then give you the probability distribution. There's a distribution, but it's adds to 1. Adds to 1. Is it? So that's the difference between the sigmoids. Sigmoid is also probability distribution, but if you add them all, it's not 1. Okay. So softmax. Okay. So it's the last layer, and after that, and in TensorFlow, you can also get a report for your model. Okay. So here is a model summary, and if you do model summary to give you more information, is it okay? Then we know first the convolution, is it? And it also gave you the shape and the number of parameters for training, is it, for tuning, and then max pooling, is it, and give you the shape, is it? And if you recall, why here there is no parenthesis 0? If you recall, because max pooling is either maximum value or mean value or some other pooling approach, it doesn't involve training weights, is it? So that's why over here, parameter is 0, okay? Then we do flatten, so similar, okay, similar. And over here, we do dense, is it? So for the dense, then we have parameter, is that we have parameter. And the dropout here, we also add. So dropout is based on the pre, so it's not involved with the weight training, is it? And the last one is also dense, so that's why it involves parameter training, okay? So this is quite useful, is it? And you can also save your model, okay, to as some file, okay? So that's a plot model, so that you can visualization, is it? Okay, and then what next? If you recall, because this is in TensorFlow, the TensorFlow. So previously, it's all regarding the convolution pooling, and then flattening and fully connected, etc. But then we still use gradient descent for the training, etc. And if you recall, so basically previously discussion is kind of feed forward. So in neural network, etc. So from the training data all the way to output, so that's a feed forward to do training, etc. And then you get the predicted result. The training one, as the hat one. And then we need to know the error between the hat one and the real target. Is it? We need to know the difference between these two. Is it? And this two, then we have the error. But that's purely for the output. Is it the error? Then we need to do back propagation. And using gradient descent to update the weights. If you recall, that the weights updates, it's because if we purely use our cost function versus weight, it involves too many metrics multiplication. And because we can also see it's very complicated, so it's not going to be efficient. So that's why we use back propagation from gradient descent, and we can find the simple calculation as they compare with the forwarding way as to update the weights. Okay, so that's the idea here. Okay, then in this case, we also needed to choose the optimizer. So Adam is one of the efficient optimizer for gradient descent. And we also needed to choose what is the cost function, or we call it loss function. In neural network, a lot of time we use this sparse categorical cross entropy. If you recall the cross entropy, and you can also specify the performance measuring matrix. So here we use the accuracy. Okay, so after that, then you can start to do the model training with the training data. And here, because a lot of time, especially if you think about image data, the size is very, very large, And so that's why it's good we use stochastic. So stochastic gradient descent, so it's batch processing. No, stochastic is the online one. Is it online one? And it's so on demand, one by one, But generally we don't do one by one, we do mini batch. Mini batch, So that's why here we also specify batch size, for our model training, okay. And after that, then for our testing data, then we can collect the loss and the accuracy. And if you recall, and who knows the answer? So generally speaking, if a model is good, in machine learning, and because here it involves training epochs. So suppose we have graph. So this is training epoch, so number of epochs. Is it? Suppose this is a loss, and the other one is also number of epochs. And here is accuracy. So what do you think? The model is good. So if model is good, if I have something, something like this, and I have something like this, is this going to be a good model? So who knows the answer? Does this represent a good model?
No, it doesn't.
Yes, no, it's not, is it? The loss should what? Loss should increase or decrease with the number of the epochs increasing. Generally, idea, loss should going up or going down. Anyone?
It should go down.
Yes, very good. Okay, loss should going down. So if you have a model, the loss going down, that means you are on track. The model is on track. How about accuracy? Accuracy should going down or going up? Accuracy, the trend.
Should be going up.
Yeah, should moving up, etc. Then this means your model is good. Okay, always keep this in mind. Okay, because those are general when you do any of machine learning model, etc. Don't report the wrong way. Is it okay? So we can see in this case it says the accuracy is pretty good. Is it okay? Because a model is pretty good, then you can try to make a prediction that with the first one, and then you can predict. Is it? And with that, how do we know which one it is? Because this one will only give you probability. Is it because it's why? Because it's a softmax. Softmax will give you the value between 0 to 1. Is it? So you don't know it's 0 or 1. So that's why here you use the argmax. Then to find which class it is, that is which basically in this case digit it is. Okay. Okay, so that's the this example. We are done, and then next let's take a look at the other example. And this example basically it's from TensorFlow. Okay, so TensorFlow has this image regarding convolutional neural network. And over here, our example is the very, very basic one, okay? And TensorFlow, it uses a different, not MNIST, it uses different images. Basically, it's a fashion. Is it? Oh, not fashion, maybe because it's an animal one. Let's double check, okay. But anyway, this is a different data set, okay, not the MNIST one. And similar is that we still use Keras, okay, high level. Always keep this in mind, okay. Keras is TensorFlow's high level API. You don't want to go with the low level, okay. Generally speaking, if maybe you PhD, you can go with the low level, okay, because you may want to build your own network from scratch, the graph, etc. And generally for application, we can just use a high level. So we can see high level, it's much more efficient as it compare with the low level one previously we discussed. Is it? So this is a high level API, okay, always keep this in mind. And we want to import layers and models, okay, here be careful. So that data set is already available, okay, so we just loaded the data, same thing, we needed to bring the value. It's also regarding image 2, 0, and 1. Oh, this one is not just animal, it's regarding different objects. Okay, airplane, automobile, bird, cat, deer, like a shaped truck. Okay. So it's kind of based on MNIST, as it only has 10 images, okay? And it also, is it 10 images? Yeah, 10 images. It also gave us the a brief look of the, and is it, yeah, 10 type of image, is it? So then classify, okay. Okay, and then over here, we also going to use convolutional neural network. Is it? So here it says convolutional base, basically use a common pattern. Is it? So it's a stack of convert 2D and pooling 2D layers. Okay, 2D layer. And their output, we already see it's a 3D, three-dimensional tensor, is it? And the shape is height, weight, and channels. Okay, channels. And the height and the weight, so basically the 2D image part, going to shrink as we go deeper into the network. Okay, but the output channels, okay, output channels, generally speaking, is going to increase. Okay. Okay, so that's the concept. And the rectified linear activation function, the ReLU, we already learned, is it? So we don't need to repeat. Okay, then let's see. So over here, we still use sequential, then we add layer by layer, is it? So the first we add a 32, and the input in this case, the third dimension is already three. There are three channels. Okay, so it may be like RGB, the different color channel, etc. So if you have red, blue, and green, that RGB, the red, green, and blue, etc. channel. And the filter size is similar. Activation, okay, we still use the same. And then we do maximum pooling, decrease the size by 2, is it? So that's this part. So this is, this 2, you have one convolution base, is it? And next you can see we have another one, is it? So now it increase the channels, is it? So channel size increase, is it from 3 to 32, now to 64, and then 64. And then we do maximum pooling, is it? Then we do 64 again, okay? So this is the model, okay? So we can also take a quick look of the model, okay? The output it shows us. But just with this one, oh, then we can also see this interesting information, is it? Okay, so we can see initially it's 30 by 30, is it? After the layer we just added, then it's decreased to 4 by 4, is it? But the third dimension increased to 64, as it 64. Okay, so now it's 4 by 4 by 64, as a by 6. So we are going to do flatten, then we do the convert it to one-dimensional, as it, and then to output, as it to output. So it's, you can see it's also similar as it to our previous one. Then we can also, then what's the next step? So all of this previous step is to define model. The model, as it, it's, be careful, okay, it's layer by layer. okay, layer by layer. And we also convert from 3D to final 1D, is it? Because for neural network, after all, you need to get it to 1 dimension, okay? And then after that, so this part is for gradient descent. Is it to find the optimized weights? Is it? So we use ADA, okay, and the loss we can define, we use cross entropy, and the metrics we use accuracy. And then we can do the model training, is it? And you can also specify the number of iterations, is it? And also over here, it combine the validation also, okay, the testing part also, okay. Okay, and it's 10 iterations, is it? And then we can also see it's a loss, you see. Initially it's 1.5-ish. The last stats 0.6, so the loss is decreasing, is it? And the accuracy is increased from 0.4 to 0.78, is it? It's increasing, okay. See, overall the trend is good, is on track. But of course, you may see this accuracy is not good, but you will see, basically, it's not an easy job. You want to get to a 90% accuracy, okay? So it's a little bit of hard, okay? Because for image processing, it's quite impacting factors, okay? And we can also collect the history data, we call it, is it? And the information that we can collect, and then we can, based on each of the iteration, we can collect loss, accuracy, validation loss, and validation accuracy. If you recall, then we do the plotting, is it, based on the training one and the validation one, the training one and the validation one. And if you recall, previously we called that learning curve. Learning curve, is it? So learning curve is if you have something looks like this, is it? So one is training, is it the validation? Then and this is this suppose it's accuracy, okay, and it's not too low, maybe around 70%. Then if the discrepancy between this is not too large, then that means the model is good. There is no overfitting issue, is it? So that's so. With the collecting of the, so here is number of epochs. This data, then we can plot learning curve, is it? So learning curve can also visualize, help us to identify if the model is good or not, okay? So over here, we can do the plotting, is it? And from this plotting, you can kind of see the model is not that ideal, is it? Because here is the accuracy, here is a validation. Accuracy is that it's not like the perfect one that we prefer, is that it's not very ideal, okay? And we can also plotting the cross entropy, as that here it also gives the training and the testing result. That's also kind of not good, is it? So the testing accuracy is just around 70%-ish. It's not good. That's why there are a lot of neural network competitions. That is a competition, then see whose model is the best. That. And we can also develop from scratch. So we will skip this part, okay? skip this part. And what is the next part? Basically, you can see for the CNN, it involves number of the convolution, is it pooling? So then you may ask, then how can I know how to choose the number of filters, the filter size, is it how many layer I should have of those? So it is, so that's why there are a lot of model training work, is it? And there are a lot of research, and in the previous decades, so the last 15 years, is it the CNN model, we have a better and better ones. So this 2VGG, it's one of the CNN. It's kind of called pre-trained models. Pre-trained models, okay, there are all sorts of, okay, and we will just take a quick, and we also have 3VGG, okay, and what that is, and regularizing or dropout, we already discussed, is it? And there is another technique in CNN. It's called data augmentation. Okay, so data augmentation. So this is also serves for improve your prediction, the model accuracy. Is it is with your samples, you make some copies of the samples in the training data set. But when you make a copy, you will make some small random modification. So what that means? What that means? So the idea is, because especially for image, is it especially for image? Let's see where we have, especially for image. So the augmentation here, small random modification, it just means you do some flipping, shifting on your image, okay, or cropping, okay, or zooming. So some of the idea, okay, some of the information regarding those, okay. So suppose like you have an image like this you get. So the data augmentation means, okay, you may flip it. You may flip it, okay, or you may turn into a certain angle, or you may crop something, or you may make it larger or smaller. So that we call it data augmentation. And then you also add this modified also into samples. Okay, so then in this case, then we can increase. So basically, we add more scenarios, is it, for our data size. Okay, so this is the idea for data augmentation. Okay, and then next, let's see. Let's see. So right now, okay, there are some other, where is my, okay. There are some very efficient and popular packages for object detection, and it also used the concept of convolutional network. So I think it's pretty nice. Okay, if you want to get to know more information. Okay, one is called YOLO. Okay, YOLO. So keep this in mind. Okay, you can try to find it. Another one is OpenCV. Okay, it's all also related with object detection. Okay, OpenCV, it's also quite, so it's just some kind of packages, okay, and you can just go ahead directly use it, okay, because right now we already understand the concept of CNN, okay, but this not just based on CNN, okay, but there are some concept of CNN involved also in it, okay, so these are the two. And then let's see, yeah, over here. And and if you recall, previously we saw that to go back here, this color, like VGG, etc. So what are all of those? So basically, there are some, we can call them like CNN, so various, we can call them pre-built, okay, pre-trained. So we can just go ahead, basically use those, okay. So various pre-trained CNN architectures. Okay, this is basically the very first one, okay. I shouldn't just say very first one, okay. So for CNN, it's a pretty early, mature one, okay, for computer vision, okay, for computer vision. It's called the AlexNet, okay, and AlexNet, it proposed some of the features, okay, like a rectified linear unit as an activation, etc. So it has some of the feature overlapping, pooling and dropout, etc. So some of the ideas. Okay, so that's regarding that AlexNet. Then, if you recall previously, we saw that VGG, etc. So VGG basically it's a very deep convolution neural network. Okay, it's a large scale image recognition. Okay, so VGG is very deep neural network architecture. Okay, it's said with 16 and 19 layers. Okay, 16, 19 layers. And the convolution filters are 3 by 3. Okay, and what they observe, so they observe, and I think if you have time, okay, you're interested, you probably can read some of this information. It's how they using increasing that to show improvements. Okay, and also it's this discovery. It's for most of the architecture in various fields. Okay, so that's the VGG. Okay, the idea, and as to the detailed. And if you read the respective articles, you will find it. Is it so? Over here, you can see that it gives you like the definition for the block. Is it? And you can see it's then for multiple layers. Is it? And then we also have like the GoogleNet. Okay, GoogleNet is at all like inception. V1, the inception V1 says to improve the utilization of computing resources, is it, by using sparse structures, okay, instead of VGG's fully connected neural network, okay. So that's, and also over here to give us some idea, okay, about this GoogleNet, okay, the architecture level. Okay, so anyway, so there are multiple, there are quite a number of various things, and also ResNet. Okay, ResNet. So this is, they said it's 2015 winner, okay, in some neural network image related like conference or competition. And it also gives you the idea, okay. So it's just, you use different configuration for your convolutional neural network. Okay. Okay, so that's all of the basic information. Okay, the convolution network itself is quite complicated.